Hello world, have you ever wondered why training deep reinforcement learning models takes so long? Well, me too. In our latest paper, we've explored this question under the angle of interference and generalization in temporal difference. Let's start with interference. Interference refers here to how taking a gradient step affects a model's predictions. Think of it this way. When taking a gradient step with the information from one example, say x1, all the parameters are changed a bit. This changes the prediction for x1, but also for any other input, say x2. In fact, the prediction for x2 changes proportionally to the inner product of these two gradients, depending on the learning rate. If this product is positive and f is a loss function, then we say that we have constructive interference, because learning about x1 informs us about x2. If it is negative, then we have negative interference. If it is 0, then a prediction at x2 is not affected. Note that this quantity arises from a bunch of previous works, but at its core it's simply the first-order term of a Taylor expansion of f around theta. In particular, in supervised learning, a similar quantity, the angle between gradients, has been called a stiffness. And it's been observed to go to 0 as soon as a deep neural network starts overfitting, or going into memorization mode. A way to think about this is that during memorization, each example is assigned a set of parameters, and so gradients for different examples become distinct. This has led some people to see a lack of interference as a symptom of poor generalization. Now in this paper, the first question about interference we ask is there anything in particular about TD that makes it so different than supervised learning? Is generalization affected? To measure this, we compared classifiers trained normally with agents that are trained to classify images by progressively scanning over the image and predicting a class. We ran hundreds of experiments, each with a varying number of training examples and a varying capacity. And then, for each training set size, we look at the correlation between the interference rho and the generalization gap. This is kind of a way to measure what happens in the overparameterization regime. What we find is quite interesting. In the supervised case, there is a positive correlation, while in the RL case, which uses TD learning here, there is instead more often than not a negative correlation. We can repeat this for many datasets, even for regression tasks, and find the same difference. Interestingly, the few experiments that we ran with policy gradient methods had entirely different behavior. So what does this mean? One way to understand this result is that TD thrives in low interference solutions, in the sense that it is happy to memorize information about the states that are visited. This creates low interference but high generalization gap solutions. On the other hand, in supervised learning, interference is a different behavior, where examples of the same class become overaligned as overfitting occurs. Now, let's go look at a more conventional RL problem, Atari. Earlier I mentioned that interference between two states measures how taking gradients at one state affects the prediction at another state. Now, turning to RL, we're going to measure how taking TD gradients at one state affects the TD error at other states. In particular, we're going to look at the states right before and right after. The two plots that you see here measure how much the TD error was reduced by an update using the state at offset 0. On the left, we show this for 3 different supervised learning tasks where we try Atom and RMS prop. On the right, we show the same measure but for 2 RL tasks, policy evaluation of an expert's trajectory and control, which is just learning from scratch to maximize reward. What's incredible is that you really have to zoom in to see the gain in the RL case. Honestly, that was quite surprising to us. The fact that TD methods require more samples than supervised learning isn't necessarily surprising, but even with the same data and the same final targets, which here is the true value function, it's not clear why TD updates lead to parameters that generalize so much worse than in supervised learning. Another surprising thing is RMS prop, where it seems that for neighbors of the updated state, the value function is almost unlearned on average at each iteration. So what's causing this? One hypothesis that we had was that if you look at the value that's being predicted by a random neural network along a trajectory, it kind of looks like this. It's not very smooth, presumably because of the high capacity of the architecture. Now if you think about it, what happens if you try to tell the prediction at one time step to match the prediction at the next time step? Well, it will try to correlate its inputs with the next target, v prime, but on a larger scale, none of the targets are ever correlated, at least at initialization. In deep learning, when inputs and outputs aren't correlated, gradients tend to become orthogonal. So what we're probably seeing here is that TD0, in a way, pushes gradients to become orthogonal. We can actually verify whether this is true in two ways. First, we can see what happens to TD lambda. If you're not familiar with it, think of TD lambda as a way of smoothing all these wiggles in the value function. Second, we can look at the correlation between how much wiggles there are and an agent's performance. Back to this later. So first, let's look at TD lambda. Again, if you're not familiar with it, the lambda parameter controls how far into the future you look in order to reuse your own predictions. And that has the effect of smoothing the temporal difference target that a neural network has to regress to. Let's look at the results. In this case, we can clearly see that increasing lambda not only makes gradients more coherent locally in time, which you can see on the left figure, it also makes the TD loss decrease faster for states surrounding the update sample. These results suggest that making a model less dependent on a single high-variance self-made target makes it generalize much more. Let's now look at some other evidence of this phenomena by going back to this high variance in the approximated value function. Now, what we're going to look at is how consistent the sign of the TD delta v minus v prime is. Here in red, we see the negative TD deltas, and in blue, the positive ones. What we're going to measure next is the average local variance of those signs. Now, what's interesting is that across many runs, the sign variance correlates positively with gradient interference, but negatively with performance. Remember that in Atari games, memorization is an effective strategy because Atari is fairly deterministic, even with sticky actions. So the fact that low interference and low sign variance is aligned with high reward is consistent with our hypothesis so far. What's a bit more surprising is that low interference correlates positively with sign variance. We still don't have a good explanation for it. Another interesting observation is that by repeating this experiment, but lowering the learning rate by a lot, here 10 to the minus 5, this effect mostly goes away, which indicates that this phenomenon is linked to an instability in optimization. Speaking of optimization, what can we say about TD's interaction with gradient descent? One interesting observation we make in this work is how gradient interference itself has very different dynamics under TD than for regression. In fact, if we compare the evolution of interference for TD and regression by looking at the time derivative of interference, we get this decomposition. Note how for TD we get these two extra terms, rho A'B and rho B'B. These terms represent interference terms between the two additional states, the target states in the TD expression. Without going into too much detail, their presence means that the variance induced by errors in predictions will be much larger when a high-capacity, high-variance function approximator, like a neural network, is used. Measuring these quantities, we actually see that depending on the type of bootstrapping used, they become quite high variance and ill-conditioned compared to regression. So, to recap, we observed that generalization dynamics in supervised learning and temporal difference-based learning induce different parameterizations. We observed that in benchmark RL tasks, TD-based methods also learn parameterizations that don't generalize as well as their supervised counterparts. We find a link between the complexity and variance of TD targets and interference, and highlight the generalization potential of TD lambda. Finally, we do a little math, suggesting that having better optimizers for TD might improve things quite a lot. For more, check out our paper, Interference and Generalization in Temporal Difference Learning.